our lesson today, we begin to study Chapter 6, the electronic structure of atoms. We do have a great deal of background knowledge from our first year of chemistry in writing electron configurations, but now we delve a little bit deeper and go back into the mathematics. What happens when one turns on a neon light, for instance? Those electrons in the neon atoms, they get excited and jump to a higher energy level by that electricity. They'll emit light when they drop back down to a lower energy level. That pleasing glow that results is explained by one of the most revolutionary discoveries of the 20th century. It's called the quantum theory. This theory explains much of the behavior of electrons in atoms, and we will see that the behavior of subatomic electrons is quite unlike anything we've seen in our macroscopic world. In our chapter, we will explore this quantum theory and its importance in chemistry. We will begin by looking more closely at the nature of light and how our description of light was changed by the quantum theory. We will explore some of the tools used in quantum mechanics, this new physics of the 20th century, and it's been developed to describe atoms correctly. We use the quantum theory to describe the arrangements of electrons in atoms, what we call the electronic structure of atoms, 1s2, 2s2, and so forth. The electronic structure of an atom refers not only to the number of electrons in an atom, but also to their distribution around the nucleus and to their energies. We will see quantum description of electronic structure of atoms and help to understand the beautiful arrangement of elements in the periodic table. Why, for example, is helium and neon unreactive gases? Why are they unreactive, whereas sodium and potassium, they're both soft, very reactive metals? This chapter will lay a strong foundation for the chapters that follow. We'll see the concepts of quantum theory being used to explain trends in the periodic table and the formation of bonds between atoms. So a very strong foundation for several of the next chapters coming our way. We begin our lesson in Lesson 1 by studying closely the nature of light. Light as radiant energy, or we'll call electromagnetic radiation, has wave-like properties, and so it's characterized by terms called wavelength, frequency, and speed. In this section, we either for the first time learn about the relationships between frequency and wavelength as related to light, or perhaps you'll review from your physical science studies. Much of our present understanding of the electronic structure of atoms comes from the analysis of light, either being emitted or absorbed by substances. To understand electronic structure, we first learn about light. The light that we can see with our eyes, it's called visible light. It's an example of electromagnetic radiation. Because electromagnetic radiation carries energy through space, sometimes we also hear it called radiant energy. We know that there are many types of electromagnetic radiation, just all in addition to what we can see within visible light range. These different forms, such as radio waves that carry music to our radios, the infrared radiation of a glowing fireplace, the X-rays used by a dentist, may seem very different. However, they all share certain fundamental characteristics. All types of electromagnetic radiation move through a vacuum at what's called the speed of light. Let's examine the parts of a wave. We'll take a cross-section of a wave and examine terms called the wavelength and the frequency. Now notice the wavelength when we measure from a top of the, so here is the wave, one wavelength, measured either from the base of the trough to the trough or from the crest to the crest. And the wavelength will be measured in a unit called the meter, which gets abbreviated with a small m. Now this abbreviation is a Greek symbol. It's called lambda. kind of an upside down Y, isn't it? The Greek symbol lambda is used to denote what's called the wavelength, and we'll define the wavelength as the distance between two adjacent peaks or the distance between two adjacent troughs, measured in meters. The frequency is the number of cycles in 1 second, so it's a timed event. If this is our specific spot, we want to know how many troughs come through this area in every second. We measure this in a unit called the hertz. Typically, I see that capitalized, hertz. Hz is how we see that abbreviated. More commonly, you might see the hertz written in a per second. Now notice what we've done. Second raised to the -1 is the same as writing 1 over every second. How many cycles per second is defined as a hertz? We can see frequency in this slide. As the wavelength increases, the frequency decreases. Here we have a shorter wavelength, but an increased frequency. Here again we have a shorter wavelength, but an increased frequency. So I am looking at this slide and just reminding us of the relationship between frequency and wavelength. As the wavelength shortens, the frequency increases. We call that an inverse relationship. As one goes up, the other goes down. Longer wavelength, shorter frequency. Shorter wavelength, increased frequency. So we see this inverse relationship with the description of how light is traveling. And again, through a vacuum, we've actually measured its velocity, and it is a constant known as the speed of light. Let's remind ourselves of the units just to be sure we've written that down in our notes as well. The unit of measure for the wavelength is the meter. The unit of measure of a frequency is a per second or a hertz. Those are the same thing in my mind. How many troughs or crests pass through a certain point in every second is the frequency, and literally the distance between crest to crest or trough to trough is the wavelength. We know there are many kinds of electromagnetic radiation waves, many different wavelengths and frequencies. Now let me comment here. The frequency gets a Greek symbol as well. It's called nu. It's kind of like a squiggly V, isn't it? Here's the wavelength. Its Greek symbol is called lambda, and the Greek symbol for the frequency is called nu, a squiggly V and an upside down Y. Lambda is the wavelength, frequency is nu. But here's a slide just reminding us that many different types of electromagnetic radiation exist in the electromagnetic spectrum. We have radio waves at one end, gamma rays at the other end, and all kinds of different wavelengths in between. Here are the wavelengths that our eyes can see, the visible light spectrum. But all of the variety of energies completed from the longest wavelength to the shortest wavelength, from the lowest energy to the highest energy, we have a wide variety of a spectrum of waves. Light is the only part our eyes can detect. We call that visible light, but there are other types of energy waves as well. This is probably not brand new, but a good review from our physical science days. Now notice with this slide, we see all kinds of information. Notice here we have a longer wavelength. I'll put lambda there to remind us that it's a wavelength. And where we're at here are radio waves. Some of these radio waves are 100 meters. Think about how long that is, and very long wave in the radio wavelengths. AM is longer than an FM station. Here we have some radar. We get into the infrared, anywhere from 1 centimeter, 0.01 centimeters. A nanometer, here's what NM stands for. Nano is a metric unit representing 10 to the negative ninth. So if you see NM, that's a nanometer. Here we have X-rays and gamma rays, and in this tiny region here, just this little bit of the electromagnetic spectrum is the rainbow of color that our eyes can see. Perhaps you remember the little saying, Roy, I should have made that spaced out a little better. Put them underneath where the colors actually are. Roy, B for blue, and greens, and violets, indigo, Roy G. Biv. I've kind of written that backwards since our rainbow is going the opposite direction that of our saying. Reds have the longer wavelengths, lower energy. The blues and the violets have shorter wavelengths of higher energy. Now notice here, red, about 700 nanometers would be a great approximation of the wavelength of a red color. Here we have 400 nanometers as the wavelength of the higher energy violet color. Wavelength in the spectrum was very short gamma rays to very long radio waves. Notice the color of the visible light can be expressed quantitatively by wavelength. Quantitatively, from reds to violets. As the wavelength lengthens, we get over to the oranges and reds. As the wavelength shortens, we get to the blues and the violets. And the greens and the yellows lie somewhere in the center of our rainbow. The speed of light has been mathematically determined in a vacuum to be 2.998 times 10 to the 8th meters in every second. We will use the constant for the speed of light as 3 times 10 to the 8th meters per second. Now notice this is the unit of measure for the speed of light. It's a velocity. Speed is a velocity, isn't it? How fast is it moving? In every second, it can go 3 times 10 to the 8th meters in a vacuum. In other words, it can't hit anything and change its speed of course. It gets a letter to denote a constant, C for constant speed of light. And mathematically, the speed of light is equal to the wavelength multiplied by the frequency. The speed of light can be calculated by taking the wavelength and multiplying it by the frequency. C equal lambda times nu. Shall we try an example? Just a little algebra formula here, no big deal. Let me give myself some more room as I'm trying to do, and we'll work out our first example problem. What is the wavelength if I have a frequency equal to 5.89 times 10 to the 5th hertz? And remember, hertz can also be written as a per second. Second raised to the -1 is called a per second. Our constant is something we'll work to memorize for the speed of light, 3 times 10 to the 8th meters per second. We know the algebra formula, C equal lambda nu. C is a constant, always 3 times 10 to the 8th power meters per second. It's worth remembering that since the speed of light constant is in a meter, our answer will come out in a meter for wavelength. And if I'm given wavelength, I must be sure that wavelength goes into our problem as a meter. So 3 times 10 to the 8th, I'm solving for lambda, and nu is given to us as 5.89 times 10 to the 5th power per seconds, or hertz. Lambda will be solved for by taking C divided by frequency. Would you hit that with me on your calculator? Let's be sure we get a common answer for our question. 3e, that's how I do my scientific notation, 3e8 on our calculator screen, divided by 5.89 e to the 5th power, 3e8 divided by 5.89 times 10 to the 5th, and the wavelength comes out to be 509.34, and I can write per second or a hertz. No, that's bad. Thank you for helping me catch that. We're looking for wavelength, so that comes out in a meter. Put a meter in for the unit of C, we get a meter out for the length of the wave. Let's try the other one. This time we're solving for the frequency. What is the frequency of blue light with a wavelength of 484 nanometers? So here we have a different problem now. Let's give ourselves some more room. Speed of light is given to us always. It's 3.0 times 10 to the 8th meters per second. The wavelength is provided for us, but it has a unit there, nano. Now remember, nano is a metric unit, 10 to the -9th power. So you can remember this as just saying like 1 meter equal 1 times 10 to the negative. No, I have that backwards. I should start that over. Sorry for the eraser here a couple times. 1 times 10 to the -9th meter equal 1 nanometer. That's what we need. So what I like to do, friends, is simply write 484 times 10 to the -9th nanometer. This nano part is taken care of by simply writing out its expression as 10 to the -9th. Now I don't worry about sliding decimals. 484 times 10 to the -9th meters is an easy way to write 484 nanometers expressed in the meter term. We're solving for frequency, the nu part of our variable, the Greek letter nu. So again, we simply divide 3e8 divided by 484 e -9. And see if you get a common answer. Please hit, don't wait for test day to start making your calculator your friend. 6.198, we should make that 6.20 times 10 to the 14th power hertz or per second, either way. Let's flip our page and read a next example. The yellow light given off by a sodium vapor lamp used for public lighting has a wavelength of 589 nanometers. Wavelengths are often expressed in nanometers just to make the number easier to report. A nanometer is 10 to the -9th. What is the frequency of our radiation? C equal lambda nu. The speed of light constant is equal to the product of wavelength times frequency. Since our speed of light constant is given to us in a meter per second, the wavelength must be coming as a meter. So simply write that out as 589 times 10 to the -9th unit meters. It's an easy way to exchange the nanometer into a meter. Let's solve for the frequency in a per second, or the same thing as saying a hertz. 3e8 divided by 589 e -9 power, and our frequency is given to us as 5.09 times 10 to the 14th power per seconds. We have a next example. By the way, I'm doing many of your homeworks with you right here in our notepad. A little practice algebra. This problem gives us a laser used in eye surgery. It's used to fuse detached retinas. It produces a radiation with a wavelength of 640 nanometers. What is its radiation frequency? Work ahead of me. Pause the video, work ahead. See if you get a common answer as I do. When ready to check your answer, turn the video back on. Pause, work it, then press play. Let's see how you did. Our speed of light constant, 3 times 10 to the 8th meters per second. The distance that light goes in every second in a vacuum is called the speed of light. The wavelength provided is 640 nanometers. That's the -9th power of a meter. Let's calculate the frequency, which will come out in a per second. You hit 3e8 divided by 640 e -9, and you found an answer. I think I have a calculator error. Let me hit twice to be sure. 640 e -9. How about 4.69, rounding to 2 decimals, 4.69 times 10 to the 14th power per seconds, or the term hertz. You've got these, don't you? Next series of examples are same algebra. We'll be very good at these by the time we're done working our samples. An FM radio station broadcasts electromagnetic radiation at a frequency of 103.4 megahertz. Capital M is 10 to the 6th power on our metric system. So this would be the station you tune into. 103.4 is some FM radio station bringing you music. What is the wavelength of the radiation? We have 3.0 times 10 to the 8th power meters per second, our speed of light constant. That's equal to the wavelength, which is 103.4 megahertz. So see what I'm doing to turn that distance into, we want to calculate the wavelength. Oh, Linda. Here's the wavelength. I was writing it in the wrong spot. We want to turn this into a frequency unit of a per second. So 103.4 megahertz has to be written as 103.4 times 10 to the 6th per second. Now I've got my variables in the familiar position. C is equal to lambda nu. I didn't want to flip those around to make you think I was writing the wavelength in that position. Speed of light in a meter per second. So I had to make sure that I was reporting my frequency in a per second. So I took care of that by saying 103.4 times 10 to the 6th to get rid of the mega and keep it in simple terms of in every second. Let's hit and see what kind of wavelength this comes to be. 3e8 divided by 103.4 e to the 6th power, and our wavelength is 2.9. And we'll carry that second decimal, 2.90, and it will come out as a meter. What is the frequency of radiation that has a wavelength of 955 micrometers? I'm trying to put in as many little metric units as we possibly can. Micro actually has a Greek symbol too. It's called mu, M-U, kind of a squiggly U, whereas nu was a Greek symbol, a squiggly V. That was frequency. You're learning a lot about the Greek alphabet with our metric system. A micrometer, a micro, is a Greek letter, mu, kind of a squiggly letter U in our American alphabet. And a micrometer is 10 to the -6th power. So 3.0 times 10 to the 8th meter per second is our speed of light constant. It is always equal to the wavelength times frequency. Here we're given the wavelength of 955 micrometers. Micrometers taken care of with that -6 power. When we solve for frequency, it will come to us in a per second. 3E8 divided by 955 E -6. And did you find the same as I did? 3.14 times 10 to the 11th power per second. One more in our set will finish the examples, and we've done quite a few of our homework problems as well, making the assignment go very smoothly for you. Let's accomplish the last one together. We want to know wavelength that has a radiation frequency given to us directly as a per second. C equal lambda nu. Speed of light is a constant, 3.0 times 10 to the 8th meters per second. Let me also just stress units in the problem, units with answer. I'm just reminding us of our criteria for credit for homework. Criteria for credit for homework says every time I have a mathematical problem, I have to show the work, including units in the problem and with the final answer. Here we're looking for wavelength. When the frequency is given as 5.50 times 10 to the 14th per seconds. Simply divide our speed of light constant, 3E8, divided by 5.5 E14 for our frequency. Here we have quite a short wavelength. We have it as 5.45 times 10 to the -7th meters. Keep in mind that if you see a number expressed like that, you might also see the correct answer written back in nanometers. 545 nanometers would be the same answer, just expressed with the nano term. So I'm saying, for instance, when you take your multiple choice quiz on lesson number 1, if your calculator is reading in a meter, which is to the -7th power, slide it 2 spots over and you'll have the -9th power, and you might be able to correctly find your match with the nanometer unit. Good work, friends. We've got lesson number 1 under our belt, a simple reminder of light and how to calculate the relationship between wavelength and frequency. Hidden in here really is a metric review. If you're given any other type of unit other than a meter or other than a per second, be sure that you're writing those in the expression with those base units. Very important to review those metric terms. I'd like you to complete your lesson number 1 and submit that. And secondly, your quiz could be started as well, the multiple choice section. Lesson number 1, quite simple, straightforward algebra, keeping in mind that it's laying the foundation of the quantum mechanical theory. What does all this have to do with the behavior of electrons? Well, that's coming in our next lessons.